Good morning and welcome back to Tech 259 on Monday, March 1st. It's the first day of a new month. I think mentally I always like to kind of make note of that, especially in the winter time, because it feels like I just need to kind of like trudge along and get through the winter and look forward to spring. So getting through February, that's a pretty big accomplishment. It's a short month, but it always feels long to me. It always does every year. So I always think it's a momentous occasion to make it to March 1st because March, it's kind of the first month of spring. It usually doesn't really feel much like spring until at least mid-March. But we're getting there. We're almost to spring, and I like spring and summer because it's nicer out. I like to be outside. I like to get solar energy from my solar system. So all of these things are coming soon. They're just around the corner. But in a more immediate note, we have an exam coming up on Wednesday. It's the first exam of this class in the semester, first of two. And this is going to be about all of the thermal energy topics that we've talked about so far. Basically everything that we've talked about so far in this class. What you are going to want for the exam to have with you, you're going to want to have your lab manual with you. You're probably going to want to have all of your homework problem sets with you so that you can refresh your memory on some of those topics. You're going to want to have a calculator because there are definitely going to be some calculation problems, kind of like the homework sets. And even though the exam is going to be on ReggieNet, you still are going to want some kind of writing utensil and a scratch pad or two, some paper to do calculations on. I would strongly advise against trying to do these calculations in your head. Even in your head, but using the calculator, I would really suggest writing these down because the more care and thought you put into doing the calculations, the less likely you are to make a silly mistake. Silly mistakes will happen if you try to do a bunch of it in your head. So I recommend writing down the equation, plugging in numbers, canceling units, and then plugging it into your calculator. All right. Basically, you can pretty much use any resources you want except for each other. That's the big thing. You can't use each other. I don't want to say too much about that, but suffice it to say that ReggieNet provides a lot of information. And so if I wanted to, I could go in and I can look at when you entered all of the answers and obviously what answers you entered. So it's not that hard to determine if two people were working together because you can just go in and you can see what time everyone entered their answers. So if people entered the same answer at the same time, then it's pretty obvious that they were working together. So let's not even go down that road. Just take it independently by yourself and we'll all be fine. All right. So more about the exam. It's going to open at midnight on Wednesday, March 3rd, and then it will close at 11:55 p.m. that same day. So you have almost 24 hours, but you have to pick a window in there to do it because the time limit is going to be 3 hours. So once you start, you have 3 hours to do it, which should be plenty of time. I don't think that should be a big stressor. It's, of course, designed so that you can't go back and watch all the videos. You have to have been keeping up with the class. But if you need a refresher and you know where to look in the lab manual or even going back to the videos, there's enough time for you to do that. But you can't take all day to do the exam. So you have 3 hours to do the exam. And that 3 hours has to be between 12 a.m. that morning and 11:55 p.m. at night. All right. I haven't set up the exam yet. I haven't written the exam yet, so I don't know exactly how many questions there are going to be. But I would say probably on the order of 40 or 50. But it depends on precisely what the mix is. There will definitely be some true, false, and multiple choice questions. And there will definitely be some calculation problems. But I know that obviously the more calculation problems that I give you, the fewer overall questions I can give you. Because I know that some of these homework problems that we've done have taken a fair amount of time. So if I give you some calculation problems, then I'm not going to give you as many questions overall. And the more calculation problems I give you, probably the fewer overall questions I'm going to give you. So I would expect, somewhere between 40 and 50 total questions, and probably somewhere on the order of between 4 and 8 calculation problems of some sort. So something in that ballpark is what I would expect. But that's an approximate number. It's not an exact number. That's an approximate number, just based on kind of what I anticipate doing as I set up the ReggieNet exam. All right, so that's about all the overview of how the exam is going to look. What would I suggest reviewing for this? Well, we'll talk about the topics in just a minute, but basically there are two kind of types of questions. I can ask you kind of conceptual questions, and I can ask you calculation questions. So for the conceptual questions, the best things to review are the lecture videos and the lab manual. And the slides. So basically the things that we've talked about and discussed in class. For the calculation problems, the best review for those are the homework problems. I design and write those homework problems because I think they're very good review for the material that we've covered in class. So there's a pretty good chance that any calculation problems I give you on the exam are going to be somewhat similar to the homework problems. So I would go through and make sure that you understand all of the homework problems. And if you have any questions, let me know, or go back and watch those review videos. All of those homework reviews have been recorded and they're all posted on ReggieNet. So you can go back and you can watch any or all of those that you want to. So that's basically how I would kind of recommend studying. For the conceptual questions, it's kind of all about the material we've discussed and talked about in class. For the calculation problems, it's all about the homework problems. So with that, now I think I'll switch over to my slides and we'll talk through the topics that we have discussed so far in this class. All right, here is a review of the material that we've covered so far in the course. So first of all, we started out by talking about energy and power and work, and we had equations for each of those. For example, we had energy equals power times time. We had work equals force times distance times cosine theta. And we had power equals current times voltage, or power is also the rate at which energy or work is done. So we had some calculations and we did some examples of those in the first homework or two. And then we talked about a general overview of steam plant configurations, and also thrown into there, we talked a little bit about energy consumption in general. Per capita energy consumption, as well as the total energy consumption in the United States. And then we talked about just an overview of how steam plants are kind of put together and what are the basic components of steam plants and how they work. So we talked about those components, and we talked about some modifications, for example, like superheaters and reheaters and feed water heaters, things like that, that make the steam plant a little bit more efficient. So this was pretty much all qualitative, though. There wasn't really any equation to speak of in this part. And then we talked about calorimetry and phase changes, which just means keeping track of the energy that is added or subtracted to a system as it's heated up, or it's boiled or condensed or frozen or melted, as there are phase changes. So we talked about the difference between sensible heat and latent heat. Sensible heat is when there is no phase change. And in that case, you can use the equation Q equals MCAT. The amount of heat added or subtracted is equal to the mass times the specific heat capacity times the change in temperature, delta T. We also talked about the difference between two different kinds of specific heat capacities, that is C sub P, the specific heat capacity at a constant pressure, versus C sub V, the specific heat capacity at a constant volume. For solids and liquids, it doesn't matter, they're the same thing, but for gases, they're different. And C sub P is always greater than C sub V. So you have to be careful when you're doing these calculations with gases. You have to use either C sub P if this process is at a constant pressure, or C sub V if this process is at a constant volume. And they are different, so it will make a difference which one you use. Then we talked about enthalpy. Enthalpy is sometimes described as the total energy content of a system. Sometimes it's also described as the energy required to create a system from scratch. And the term that we use for enthalpy is H. The variable that we use is H. And usually we're not so interested in the total H. We're usually interested in the delta H, the change in enthalpy of a system. And the change in enthalpy of a system is equal to delta U. U is the internal energy that includes heat and work transfers. And you add to that the change in pressure times volume of the system. So like PV2 minus PV1, that would give you the delta PV, the change in pressure times volume. Okay, also remember for internal energy, when we add something to the system, like when we're adding heat to the system or we're adding work to the system, that is positive. And when we're taking it away from the system, so we're taking work out of the system, like the system does work on a turbine or something, then that's a negative from the system. So we subtract that work. And when we're getting heat out of the system, again, that's a negative. So you add something to the system, that's a positive. If you subtract something from the system, you have to subtract that. And the last thing we talked about in that day was latent heat, which means there is no temperature change, but there is a phase change. So this is when you're boiling or condensing or freezing or melting. So in those cases, the amount of heat that you have to add or take away, depending on which way you're going across the phase change, the amount of heat equals the mass times the latent heat. And L is the latent heat of either fusion or vaporization or condensation. The next day, we talked about the zeroth and first laws of thermodynamics. The zeroth law was really simple. We spent all of about 2 or 3 minutes talking about it. And it just says that if two systems are in equilibrium with a third system, then those two systems are also in equilibrium with each other. All right, that's what the zeroth law said. The first law we spent a little bit more time on, and that says that the total energy of an isolated system is constant. You can transform it from one form to another, but you can't create or destroy energy. And the equation that we use for the first law is delta U, that's the change in internal energy, equals Q plus W. And I just talked about this in the last slide. All inputs to the system are positive. Everything that you get out of the system is negative. You subtract that. What's kind of nice is if you have a closed loop, like a steam cycle or a refrigeration cycle or a geothermal energy cycle, anything that is a closed loop system, your change in internal energy around that loop is zero. It has to be, otherwise we said you'd either be heating up the system forever, or you'd be cooling it down, or it'd be expanding or contracting forever. So we know that the change in internal energy around a closed loop is zero, which is convenient because that way we can keep track of what heat is added, what heat is taken away, what work is done on the system, and what work is done by the system. And they gotta all balance out to zero through one complete loop of the system. We drew 4 basic thermodynamic diagrams for the system. We talked about heat engines, and we talked about cold heat engines. The difference was where's the ambient temperature. And we also talked about heat pumps and refrigerators as well, just at a very basic level. You know, where does the work come in? Where's the ambient temperature? Where's the heat flow? So those are just kind of like bubble diagrams where you have like the cold temperature reservoir, the hot temperature reservoir, the system, and work is either going into or out of the system. Then we talked about the efficiency, and the actual operating efficiency of a heat engine is equal to the work that you get out divided by the heat that you have to put in. So that is the actual operating thermal efficiency of any kind of heat engine. And then we also talked about perpetual motions of the first kind on that day. If they violate the first law, then they are considered perpetual motion machines of the first kind. The next day, we talked about the second and third laws of thermodynamics. The third law was super simple, and we spent 2 minutes or so talking about it. It just talks about entropy, and it says that the entropy of a perfect crystal at absolute zero temperature is exactly equal to zero. So it's just kind of a baseline reference for entropy. All right, but the second law is a little more complicated. We spent some time talking through each one of these 3 statements of the second law. And it doesn't initially look like they should be part of the same law, but they are. And I tried to do a calculation at the end of that day, if you remember, to kind of show that they are actually related to each other. And if you violate one of them, then you're going to violate the others as well. So these actually are all different statements of the same thing, which is the second law of thermodynamics. We talked about reversible systems, which are purely theoretical. In order for a system to be reversible, then there can't be any friction, there can't be any heat loss to the environment, and it has to be an isentropic process, no change in entropy. And in the real world, that doesn't happen. In the real world, all systems are irreversible to some degree or another. Entropy is kind of a measure of disorder. It's also a measure of how irreversible a process is. And we didn't use this equation very much, but I do want you to know it. If I gave you a really simple calculation, you could probably do that. The change in entropy, delta S, is equal to the heat that is transferred, Q, divided by the temperature at which it's transferred, T. And remember that T has to be in Kelvin, absolute temperature. And then we talked a little bit more about efficiency. On the previous slide, in the previous day, we had the actual operating efficiency of a heat engine, but now we talked about the ideal efficiency. So best case scenario, if everything is ideal and perfect and frictionless, then what's the best efficiency you can ever get? It's called the Carnot efficiency, and it's given by these relationships that we talked about on this day. Usually this one with temperatures is easier to use than this one with amount of heat that is transferred. Again, it's really important that these temperatures have to be in Kelvin. You'll get the wrong answer if you put them in some other units besides Kelvin. And if they violate the second law of thermodynamics, then a machine would be called a perpetual motion machine of the second kind. And the third kind, remember, is a little bit different. In order to be a perpetual motion machine of the third kind, it just has to ignore friction. So it kind of, it's the idea that, you start something spinning and it'll just spin forever. Or it's the idea that if I drop a bouncing ball off the floor, it'll come back up to the exact same point that it started. That ignores friction that is present at the interface between the bouncing ball and the floor and the deformation of the ball. So that would be a perpetual motion machine of the third kind. And we already talked about the third law. And the next day, we talked more about steam plant efficiency and about boiler safety. I enjoyed this day. I enjoy all days of this class, but I really did enjoy this one a lot. We talked about a brief history of the steam engine. You should know basically how a Newcomen engine works. Remember, that's also called an atmospheric steam engine. And then we talked about what James Watt did to improve the efficiency of the steam engine. So he did these things. You should know about these 2 things and how they improved the steam engine. All right, we talked about this before, and now we talked about how do we improve this? How do we improve the Carnot efficiency of a steam engine? Well, we want this term to be small so that we're subtracting a small number from 1. So we want either T sub L, that's the low temperature, to be small, or we want T sub H to be high. Either one or both will decrease this value this term as a whole right here. So in order to do that, we showed some phase diagrams, and we showed that you can decrease T sub L by decreasing the condenser pressure, which is why we typically operate condensers at a vacuum below atmospheric pressure. And in order to get a high T sub H, usually we increase the boiler pressure, which increases the steam pressure, and that will get us a higher temperature of steam. So both of those things will be used to decrease this overall term right here, which will increase the Carnot efficiency, which is the maximum theoretical efficiency that it could achieve. And then the last thing we talked about that day was a few things about how steam plant safety has improved over the past 150 years. Remember that video that I showed? It was a Budweiser commercial, and it showed a river boat exploding, and that was because of the steam plant exploding. So we talked a little bit about steam plant explosions in the 19th and early part of the 20th century, and we talked about some things that have been done since then to improve the safety of steam plants. Next, we talked about Carnot and Rankine cycles, steam cycles, basically, and we plotted them on pressure volume and temperature entropy diagrams. And what's kind of neat for both types of plots, the enclosed area of the cycle, you draw your cycle, the enclosed area is the work that is done by the system in one complete loop of the system, one cycle of the system. The first thing we did was plot the simplest possible case of a piston moving inside of a cylinder. That's pretty much the simplest possible cycle that we can talk about. And we plotted that on a pressure volume diagram, and we calculated the work inside of that. That was also a problem on one of the homework sets. And then we talked about how if we were going to plot a steam diagram, the simplest one to plot is a Carnot cycle. So we plotted a Carnot cycle on a pressure volume diagram, and I gave you an equation to calculate the work. It was the one with the natural log functions in it. And then we said, you know what, this is kind of a complicated diagram. It's easier to plot the Carnot cycle on a temperature entropy diagram. So we did, and it turns out to be quite a bit easier to draw and to calculate the work when you plot it on the temperature entropy diagram. And then one of the last things we did was we said, all right, Carnot cycle, okay, that's like the, in theory, the most efficient cycle, but it's not very practical. So we took it one step more practical to the Rankine cycle. So it's still very much an ideal cycle. It's reversible, it's ideal, but it's a little bit more realistic because at least now the fluid is being fully condensed in the condenser. So we're getting back to a liquid, the whole thing is a liquid at the outside of the condenser. Whereas if you recall in the Carnot cycle, we're actually stopping the condensation process before all of the fluid fully condenses. And if you need some review on that, you can look back in the lab manual to see that diagram. So the Rankine cycle uses a process where the fluid is fully condensed in the condenser, and then we plotted that on a temperature entropy diagram, and we gave an equation for how to calculate the work for a Rankine cycle on a temperature entropy diagram. And then finally, the very last thing we did on that day was we talked about some modifications to the Rankine cycle to make them more efficient and more realistic. So we talked about increasing the high temperature, T hot, and decreasing the cold temperature, T sub C, and also adding superheat, like in a superheater or a reheater or something like that. And we talked about what those would look like on the temperature entropy diagram. At that point, we moved from what I would call thermodynamics into heat transfer. And I have to say, I probably like or enjoy heat transfer a little bit more because it's a little more applied and I think a little bit more useful. It's pretty easy to see how you can use this stuff, this material, in your home, in your windows, on any type of building, anything where you're trying to either encourage or discourage heat from being transferred from one body to another body or one fluid to another fluid. So these are really practical situations. The first thing we talked about was heat conduction. And to do that, we defined a thermal resistance for conduction. For a plane wall, it was this. Remember, L is the thickness of the body that you're conducting through. K is the thermal conductivity of the material, and A is the surface area through which you're conducting the heat. For a cylinder, we had a different thermal resistance for conduction. We took the natural log of the outside radius divided by the inside radius, and we divide by 2 pi LK, where L is the length of the cylinder, not the thickness, but the length of the cylinder, and K is the thermal conductivity of the material. Then we talked about how you can add thermal resistances in series or in parallel, depending on whether the heat has to go through all of those layers, or it can go through one of those layers, or choose which layer to go through. So you can add thermal resistances just like resistances in the electrical domain. You add them in series, just add them up one to another. In parallel, it's 1 over R total equals 1 over R1 plus 1 over R2, et cetera, et cetera. And then finally, after you calculate the thermal resistance, you can plug it into this equation. You take the delta T, T1 minus T2, divide by R total, and that gives you the rate of heat transfer in watts. The next thing we talked about was convection, and we defined a thermal resistance for convection as being 1 over HA, where H is the convection heat transfer coefficient and A is the surface area through which the convection is transferring heat. The problem here is that we don't normally know H. We don't know what that is, and usually it's not obvious, and it may be given in a problem if I want to be really nice, but in general, in the real world, you don't know H. So you got to figure out what H, the convection heat transfer coefficient, is. And the way you do that is with these non-dimensional numbers. Typically, the first one that you'll find is the Prandtl number. It'll be typically given, or you can look it up. So on the exam, I would probably just give it to you. And then you can calculate the Reynolds number. This is a non-dimensional number that tells you whether the fluid flow is going to be turbulent or laminar. And if turbulent, then how turbulent is it? So remember, the equation for Reynolds number here is the velocity of the fluid flowing times the characteristic length. And remember, for a flat plate, that's just the length of the plate across which the fluid is flowing. For a cylinder, it's the diameter of the cylinder. So that's called the characteristic length. And then this term nu, this variable nu, it's the Greek letter nu, and it is the kinematic viscosity of the fluid. So once again, that you could either look up, or I would most likely give you what that is. Then once you have the Reynolds number, you can plug into an experimentally determined relationship for the Nusselt number. And that usually uses a combination of the Prandtl number and the Reynolds number to some exponent. And then once you have the Nusselt number, you can use the definition of the Nusselt number, which is this, and say, all right, now I know what the Nusselt number is. It's this number. Now set it equal to this, because you know L sub C and you know K. So now you can solve for H. So that's most of the problem. Once you know H, then you can plug it into this equation up here for the convection thermal resistance. And then once you have this thermal resistance, you can either add it in series or parallel to other forms of heat conduction that you've got going on in that problem. And then once you have R total, you can plug it back into this equation. It's your delta T divided by your total thermal resistance, and that gives you your rate of heat transfer in watts. And the last mode of heat transfer that we have is radiation. We have two different types of resistance in radiation. We have a surface resistance. Anytime a body is radiating or being radiated, we have a surface resistance, and it's given by these terms here, where this epsilon is the emissivity, which is the efficiency with which that surface can either radiate or absorb radiation. and you divide by the surface area of body I times the emissivity of body I. That's the surface resistance. Then the space resistance tells us how much of that radiation emitted by body 1 is going to make it to the surface of body 2, or I and J, as the case may be. And here we have the area of body I, that's the one radiating, times what's called the view factor from I to J. So remember, the view factor is the geometrical term that tells us how much of the radiation is going to be received by body J that is emitted by body I. So in the case of our class, I'm not going to make you calculate or look up the view factor. I'll either tell you what the view factor is, or you might have to use your knowledge of what the view factor is for some kind of intuitive cases. So the two extreme cases of view factor are if body I is entirely within body J, then any radiation emitted by body I is going to make it to the surface of body J. So in that case, the view factor is 1. The other extreme is that if body I and body J are both really like almost infinitesimally small, and they're very, 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 very far apart, then practically none of the radiation emitted by body I is going to make it to body J. So in that case, the view factor would be 0. And then there's a whole range in between where the view factor would be between 0 and 1. But if it is between 0 and 1, then I would have to give you that in the problem, because calculating that is just a little bit beyond the scope of this class. So once we have our surface and our space resistances, remember, oftentimes you would have twice as many surface resistances as space resistances, and oftentimes they're in series, but I wouldn't necessarily say always. Once you have those, you can add those up, and you got your surface and space resistance. You can plug it in here to find your heat transfer due to radiation, and this works as long as radiation is the only form of heat transfer we have in our problem. But if we do have different kinds of heat transfer occurring in the same problem, then we need to come up with a thermal resistance for radiation. And this does not work to combine with other modes of heat transfer, other thermal resistances, because the numerator of this equation is not the same. You have these exponents here. So to combine with other modes of heat transfer, we define this thermal resistance for radiation that uses the surface and space resistance, but then it also uses the Stefan-Boltzmann constant and the temperatures. Once again, a reminder, make sure that all of these temperatures that you put in here are in Kelvin. If not, you will get the wrong answer. And then once you have R rad total, that's the value you can put in series or parallel with thermal resistances from conduction and convection, or other radiation, other parts of the problem that also have radiation. So then once you combine those in series and parallel, you have R total, and you can plug that into this equation to get the total rate of heat transfer. And then one of the last things that we had was a discussion of boiling and condensation and heat exchangers. We talked about 4 different types of boiling, so you should know about that. And we have this equation for the rate of heat transfer through boiling. Once again, for boiling, I would give you the boiling heat transfer coefficient, H here, but you would have to plug in these values and calculate Q dot. We also talked about some methods, how you could increase the rate of boiling heat transfer. What are some things you could do to increase that rate of heat transfer? And then condensation, we talked about 2 different types of condensation. The equation is very similar to the equation for boiling up here. I would have to give you this H term right here, and then you could plug in these terms and calculate Q dot. And the last thing we did is talk about heat exchangers. We talked about 3 basic types or designs of heat exchangers and some pros and cons. of each. And then we solved problems with heat exchangers by doing an energy balance. And we said that, look, the rate of heat transfer in the heat exchanger is equal to the rate that heat is being gained by the cold fluid, which is equal to, in our ideal case here, we can set that equal to the rate that heat is being lost by the hot fluid in the heat exchanger. All right. This makes some assumptions. It assumes that you don't have any heat that is lost around the outside of the heat exchanger, but this is a reasonable assumption for us for our purposes. And we talked about some different designs and also some methods that you could use to increase the performance of the heat exchanger, which means increase the rate of heat transfer for the heat exchanger. All right, so that was about it. Once again, I'd recommend making sure that you review the conceptual ideas that we talked about. And the best way to do that is by reviewing the lab manual and reviewing the lecture slides, your lecture notes, if you've been taking notes during these lectures, and reviewing the slides. Then for the calculation problems, the best way to review for that is the homework problems. So make sure that you are comfortable with all of the homework problems. If I gave you a problem on the exam that is similar to the homework problems, I would expect that you'd be able to do it. It may not be identical. The situation might be a little bit different, but if it's conceptually kind of similar to the homework problems, then I expect you would be able to solve that. All right, so let me know if you have any questions. Once again, the exam will open at midnight on Wednesday, March 3rd. You have 3 hours to take it once you start, and it will automatically close at 11:55 p.m. on Wednesday, March 3rd. So make sure you don't wait to start it until 11 p.m. because it will automatically submit whatever you have at 11:55 p.m. So give yourself the full 3 hours. In other words, start at least by 9 o'clock p.m., if not earlier. That's going to be about it for today. If you take a look at the schedule after exam 1, on March 8th, that is the following Monday, is going to be a work day for you. So I designed that to be a time where you can work on your thermal energy projects. And then March 10th is going to be, well, that's our personal well-being day. So that's kind of what's left of spring break. So the next time we meet in class is actually going to be on March 15th, where approximately half of the class will give their thermal energy presentations. And then on March 17th, the other half of the class will give their thermal energy presentations. And then after that, that's the last thermal energy stuff that we'll do in this class. After that, on March 22nd and onward, we're on to a totally different subject material. It's related to electrical energy generation primarily. So we'll start that topic on March 22nd. But for now, good luck on the exam, and I'll see you next time.